Today we'll be discussing about least square solution of functions, and yeah, we'll be discussing about both linear functions and non-linear functions. I'll try to keep this reading group in English. I hope it's okay with everyone. So, let's move ahead. Uh, yeah, let's start discussing about the systems of linear equations. And yeah, this is kind of a refresher on, like, all, most of you might be already be familiar with this, but let's just go over it one more time so that you're more ready to um, take a look at nonlinear functions. So, so consider the case that we have the number of equations and the number of variables, they're equal. So we have so so we don't have less information than the number of variables, which might cause infinite solutions, or we don't have more information than the number of variables. So that might cause no solution to exist. So we have number of equations equal to the number of variables. In that case, we usually get the exact solution of the equation. So how do we go about doing this? Let's consider a system of linear equations that you are seeing on the left. I think everyone will agree that this is a system of linear equations. It's the matrix equation that you see on the right is equivalent to the system of linear equations on the left, right? Most of you might already be familiar with this, but if you're not, you can cross check easily by multiplying these two matrices and getting. So if you multiply these two matrices, you'll have a1 1 x1 a1 2 x2 to a1n xn, and you have the same thing here, a11 x1 a1 2 x2 equals to b1 equals to b1, right? So you'll get the same thing. So essentially, these system of linear equations and this matrix equation are equivalent. That's what I wanted to say. My audio is like it's correct, right? The volume and all.
Yeah, yeah.
Okay. So yeah, this matrix equation that we obtained, we can easily express it as ax equals to b, where A is this n cross n matrix, X is this one n cross one matrix and n cross one vector rather, and B is this n cross one vector on the right. So yeah, this is a very neat way of expressing a system of linear equations. If you're not familiar with it, then I think you should definitely read this in more detail. Yeah. So yeah, then you should definitely read this in more detail and get acquainted with it. It's very useful to express linear equations this way. So solving this linear equation now becomes very easy because you can just multiply both sides of the equation with A inverse on the left, and so if I show you, yeah, A inverse on the left, and the A inverse on the left cancels out with this A, and the A inverse on the right, we are left with X vector equals to A inverse B vector. Right? So this is very, like, it becomes very straightforward to solve this equation using this method. So yeah, this is what the X vector will look like. It will be A inverse into B, and you can see that this is an n cross one vector. We have an n cross n matrix over here, and an n cross one, so that becomes an n cross one vector. So yeah, the equation checks out. Okay, so yeah, that was the exact solution of system of linear equations. We can now move on to the least square solution of a system of linear equations. Do you have any doubt, like in the previous section? Anyone who was unfamiliar with it, haven't studied it before? I think most of you already had studied it before. If anyone is not familiar, you can ask immediately. Like, you don't need to wait for me to give you the chance to ask. Okay. So yeah, let's continue discussing about the least square solution of linear equations. Yeah. So in this case, we typically have the number of equations greater than the number of variables. Now, why is that? We'll look we'll look into that in later slides. But generally, that is because if the number of equations is greater than number of variables, generally it's the case that you don't find an exact solution because some of the equations are conflicting with each other. Yeah. So in that case, so before we go on to that, let's just look at the matrix equation that we expressed in the previous slide as a sum of vectors. So how do we express this matrix equation as a sum of vectors? So this is a matrix equation from the previous slide. It's nothing new here. We write it down as a system of linear equations just for clarity. So what we notice here, like you can notice that this is the first column of the matrix. This is the second column, and yeah, this is the third column, and this is the last column. So the first column is multiplied by x1, the second one is multiplied by x2, and so on, and the last column is multiplied by xn, and you get b with the b vector at the end. So you could rewrite this whole system of linear equations as either this matrix equation, or you could rewrite it as this vector equation. So yeah, this is the first column of the A matrix, the second column of the A matrix, the last column multiplied by x1, x2, xn equals to the b vector. The b vector is just the vector b1, b2, bn, b1, b2 to bn. So yeah, you can express this system of linear equations as this column, as this sum of vectors. Yeah. So what you will notice here is that yeah, this is the equation from the previous slide. What you will notice here is that B is a linear combination of all the column vectors, right? If you have completed maths 2 properly, then I think you should be familiar with the concept of linear, like vector space, span, and linear combination, linear dependence, and independence. But okay, so I'm assuming you are familiar with that a little bit. If you have any doubt, you can ask, obviously. But yeah, so B is a linear combination of the column vectors of A matrix, right? So we can say that yeah, B is a linear combination of column vectors, right? So B belongs to the span of the column vectors of A. We also say that B lies in the column space of A. I think it's denoted like this. Yeah, B lies in the column space of A. Right. So you can visualize the column space of A to be this plane, for example. In reality, it would be a multi-dimensional hyperplane, but just to visualize things, you can visualize it as a plane. So if you visualize the span of the column vectors as a plane, then B vector will be lying inside that plane. So it will be lying on that plane. That would happen if there were to exist an exact solution for the system of linear equations. But the need for the least square solution comes up when, for example, m being the number of equations is greater than the number of variables. So if the number of equations is greater than the number of variables, then you see that the column space of A will be n-dimensional. So n-dimensional column space of A, but the B vector will be m-dimensional, right? So B has much more freedom, and yeah, because M is greater than N. Because M is greater than N, B has much more freedom, and um, it can very it's very likely that it is not inside the span of the column vectors. If it is inside the span of column vectors, then you can definitely find the exact solution of this least squares. You can find the exact solution of this system of linear equations. But if it is not, then you so yeah, if B is not in the span of the column vectors, then it would look something like this. Because if this is a plane that represents the span of the column vectors, then the B vector will be something like this, sticking outward. It's not lying on that plane, right? Right. Again, if there are any doubts, you can ask me. So yeah. So what? So yeah, because now we encountered this problem that a B vector is not lying in the column space, and we have no exact solution for the matrix equation. How do we solve? How do we solve the matrix equation? Right? We can't find the exact solutions. So what do we do? So in that case, we try to find the solution. We try to find the best solution instead of the exact solution. And what do I mean by best solution? Okay, I'll explain that in a minute. So we consider this new equation. It's not really new. It's kind of similar, but yeah, it's kind of, so yeah, we consider this new equation where B star, this vector B star, it's different from the vector in the previous slide. The B vector, this vector was provided to us. This vector we don't know. B star, it's the span. We don't know it yet. So B star is the span of. So B star lies right. So we have this constraint that we choose B star such that it lies in the span of the column vectors. What did we do here? We made a new matrix equation such that the B vector of that matrix equation lies inside the span of the column vectors of A. How does this help us? So we'll try to find an X star that minimizes the distance between B and B star, while B star is being constrained to lie inside the span of column vectors. So if it was not constrained to lie in the column space, like B minus B star will just take B star equals to B, and B minus B star will be 0, and that will be the minimum. But since B is constrained to be inside the column space, it is not as trivial as that. But it's still pretty easy to figure out what B star is. Can anyone guess? I mean, can anyone tell what B star should be? If this is the column space of A, let's assume it to be a plane, and this is the B vector sticking outward from the origin, not lying in the plane. What vector should B star be such that B minus B star is minimum?
The projection.
Perpendicular. Yeah, projection.
Right. The projection of B vector on the column space of A, right? So if we draw something like this will be B star, and this will be a perpendicular, right? So what would this vector be? This vector,
B minus B star.
right? This will be B minus B star, right? So yeah, I'll have this illustrated in this slide a little better. So this B star is a projection of B. B star must be a projection of B on the column space of A for it to have the minimum distance with B. Right. So now that we know what B star is, what properties do you think B minus B star holds? We know that B minus B star is perpendicular to B, right? Can we also say that B minus B star is perpendicular to the plane, the span of column vectors? Anyone? Okay.
Yes, it will be.
Right, it will be perpendicular because we are taking the projection of B on the column space, right? So the projection of B will always have, like, B minus B star would be always be perpendicular to the plane, right? Because that's the definition of projection. So B minus B star will be perpendicular to the span of the column vectors. So what does that mean? It means that if we take the dot product of any of the column vectors with B minus B star, that will come out to be a 0. That will come out to be 0, right? This shouldn't be a vector sign here. I'll fix that later. Yeah. So dot product of any of the column vectors with B minus B star should be 0. Why? Because B minus B star is perpendicular to the column space of A, or it is perpendicular to the span of the column vectors of A, right? So this should be 0. Now what follows from here is that if you like this system of equations and this matrix equation are equivalent. If you don't believe me, you can multiply them and check. But yeah, this system of equations and this matrix equation are equivalent. You can kind of visualize it right now only. Yeah. Yeah, so you have this column vector and you want to multiply it with the B vector. How would you do that? You want to multiply it with B minus B, right? B2, B1, Bm, right? So how do you do that? The easiest way to do that is to transpose this matrix and multiply it with this vector, right? So yeah, so this system of equations is the same as this matrix equation. And so if you open the brackets and send it to the other side, you can easily again. So yeah, so this is trivial, right? This is trivial, and from here you can go to this by using the definition of B star that we um, use. So we define this matrix equation, right? You have to find x star such that ax star equals to B star. So we are using ax star equals to B star over here. We're replacing B star with ax star, and we get this equation. So now from this equation, it's really trivial to solve x star. You just multiply both sides with the inverse of A transpose A, and you get x star. So yeah, that is. So yeah, so just a disclaimer here. In reality, while solving these equations, you don't really take the inverse. There are other methods of solving linear equations which are faster. But for our purposes now, just for understanding, I think we can assume it's good enough to say that we're just taking the inverse. Right. So again, this is the value of x that minimizes so if you were to plug this x star in A, what you would get from this equation, the B star vector, the distance of that vector to B would be minimum. So so it's basically reducing the sum of squared differences between the elements of B vector and elements of B star vector and B vector, right? So this is a least squares minimization. Do tell me if any of that gets confusing. It can get confusing very quickly sometimes. So yeah, so that was linear. So that was least squares.
So here we are minimizing mod of B minus B star. So
Right.
does that also imply minimizing squared sum?
Yes, because if you take the mod of B minus B, so this will be B1 minus B1 star, right? And B2 minus B2 star. So when you take the mod, what do? You take B1 minus B1 star multiplied by B1 minus B1 star plus b2 minus b2 star square plus bn minus bn star square.
Oh, okay.
This is all you do, right, to calculate the modulus of a vector. So this is this is basically where the squares in the least squares approach lies in this method. If you couldn't, if it was not apparent, so this is where the squares are lying. Okay. So let's move on to non-linear functions now. We were discussing about linear functions till now. Let's move on to non-linear functions. And yeah, we'll discuss how to find the least square solution of non-linear functions. Before that, again, we'll do a quick refresher on how to find the exact solution of a 1D nonlinear function. I think most of you have covered this in your Maths 2 course, but maybe you have not because of the online semester, or maybe you have forgotten. So I'll just do a quick refresher. So yeah, if you're given a nonlinear one-dimensional function, how would you find the solution of that function? So
Yeah, intersection with the XL.
yeah, the most obvious way is to find its intersection with the x-axis, right? But that is the analytical way to solve the equation. If you know the equation, then you can solve it. But for example, how do I say it? So, for example, if this was not like a function like this, specifically the function of third order of x, something like this. I don't remember exactly. -1 or something. I don't know. Probably this. Yeah. But so, for example, if it was not this, it was something which was more complicated, and maybe you can't even express it in terms of x or the like.
We can use numerical techniques in that case.
Right. So yeah, that's what I was going to say. We can use numerical techniques, right? So we'll be discussing one such numerical technique. There are obviously reasons why you cannot find the solution of linear equations analytically. I'll get back to you on some of those reasons later on this current. But let's continue the discussion right now. We'll have to use numerical solutions to find the solution of that 1D function, right? So
like functions like say tan x is equal to x. I'm sorry, tan y is equal to x. Yeah. I mean, if you're trying to intersect, those two functions.
Right.
I
So you'll have to
to numerical techniques.
That's a good example. Right. So if you want to find the want to find the solution of tan x minus x equals to 0, or if you want to find the solution of this, you can't really find it analytically.
So yeah, you'll have to use numerical analysis to find the solution of that equation. So we'll move on to discussing intuitive steps so as to find the solution of a nonlinear one-dimensional function. Right. So intuitively, what do you think? What should be the steps that we should take? So I think it's fairly logical to say that we should proceed with some kind of a gradient descent. We should take some initial guess value, and on basis of that value, we should start gradient descent from that point. If you don't know about gradient descent, I'll try to link some resources where you can read more about it. But I think it should be fairly clear by the end of this section what gradient descent is. So yeah, we should you should pick initial guess, and you should start like moving along the gradient of the function so as to find the intersection of that function with the x-axis.
I think it's a fairly logical as like thing to say that you want to take bigger steps because the value of that fx at that point at your initial guess is quite large. So to reach the value 0, you'll have to take a larger step, right? And what it also depends on is the derivative of that function, the first derivative of that function. So the step size should be inversely proportional, in fact, to the derivative of that function. Because, so for example, if you have a function with a very high derivative, right? If you step even a little bit in either direction, you are covering a very large distance in terms of the y coordinate of that function, right? So you have so the step size should be inversely proportional to the derivative, and it should be directly proportional to the value of the function at your initial guess. So yeah, keeping these things in mind, this is just an intuition I'm trying to give you. I'm not gonna build anything off of it. Just an intuition, and when you later see that when you later see the equation form, you can relate it back to this intuition that we developed here. So yeah, let's discuss the approach to solve this problem, more formal approach. More formal approach is to take an initial guess, take any initial guess. The closer the initial guess is to the actual solution, the better it is. Then we approximate the function as a linear function. What does this mean? It means that, so if we have a good enough initial guess, then so for example, if this is the actual solution, and if we have a good enough initial guess, for example, at this point we have our guess is that this is the solution, then in the neighborhood of in a small neighborhood of this function, say in a small neighborhood of this point, say from here to here, the function shall behave linearly, more or less linearly, right? So in a small neighborhood of our initial guess, the function will behave linearly. So we'll assume that our initial guess is good, and we'll approximate the function as a linear function. Now we do this step because a linear function is very easy to solve for. It's very easy to solve where the line intersects the x-axis and find the roots and find the 0 of the solution of the linear function. So once we find that solution, we hope that the solution is slightly closer to the actual solution of the original function. It might be a little bit unclear now, but we'll look into an example later on, and that will clear things up. So yeah, we solve the a linear function. We approximate the function as a linear function. We solve the linear function, and whatever solution we get from that solving the linear function, we hope that it is closer to where we want to get finally, and then we repeat the process again using this new solution as a guess for approximating the function as a linear function, and then solving the linear function again. So this process keeps on repeating until we find a solution which is either at the actual solution, or it is within a threshold of acceptable values. That might not be very clear, so I think we should look at some numerics now, and then we'll look at a figure to understand better. I think most of you have studied this method, but for those who haven't, I'll be a little bit more descriptive. So using Taylor expansion, so yeah, so we take the initial guess to be x0, okay, and we want to find what do we add to x0 such that the value of f x0 plus delta x equals to 0. We want to find what do we add to x0. So we approximate this function as a linear function using Taylor expansion, and we get this. So right, this is Taylor expansion. I think everyone will be familiar with it. Now we solve this linearized function and we equate it to 0, and we obtain the value of delta x to be minus fx naught upon f dash x naught. Right? There shouldn't be a 0 here. I will correct that in the slide that I share with you. Right. So the value of delta x equals to minus fx naught upon f dash x naught. Now, if we add this value to x naught, so we add this value to x naught, and we plug it in the original function, the original non-approximated function, and if that value equals to 0 or it is somewhere close to 0, maybe h or something, then we accept the solution and we say that yeah, we found a solution, we can stop here. But if it is not 0 or anywhere close to 0, then we should keep repeating the process. We'll take x1 equals to the new solution, and we'll do the whole thing again. We'll find delta x equals to minus fx1. Notice the point at which we are finding the value of the function and derivative has changed. It has now become x1. So yeah, we'll keep repeating the process until we find the solution of the function. I think a figure will illustrate it the best. So consider this function that we saw in the beginning of the slide of this section. Let's take our initial guess, x naught equals to 2, right? Let's take this guess. So yeah, we take the initial guess x naught equals to 2. Then we find the value of the function at that point, right? And we linearize this function at this point. So at this point, we linearize the function, and we find the solution of that linear function. So we find the solution of that linear function. It comes out to be here. So you can see how this is a gradient descent. It's moving along the gradient, right? We find the solution of that linear function, and we repeat the process again, because this is at this point you can see that the value of the function, excuse me, the value of the function is not 0. So we repeat the process again. We linearize the function at that point using the gradient, and we find the solution of that. We find another point. I think it's been two iterations till now, and in the third iteration, it finds a pretty good solution of that equation, right? I think from this figure, it should be pretty clear how this method works. If there are any doubts right now, you can ask, or if there are any doubts at any point, you can ask. Okay, I think it's clear. I'll move forward. So yeah, some things to notice. One of the thing was that this is the iterative form of the method that we just discussed. Xn plus 1 equals to xn minus fxn upon f dash xn. What I want you to notice here is that the delta x, the step size of the gradient descent, is in fact proportional to the value of the function and inversely proportional to the gradient of the function, right? So yeah, the intuition that we built earlier is verified by this method. Also, I want you to notice that xn plus 1 equals to xn minus delta of xn, where delta is the function that gives you the step size of the gradient descent, right? I want you to remember this form because it will come later when we discuss about nonlinear function. Excuse me, least square solutions of nonlinear functions. Right. So we'll see this form of iterative convergence. We'll see this again later. And so yeah, for those of you who didn't know, this method is called the Newton-Raphson method. It's a very famous method of solving 1D nonlinear functions. And yeah, I think you should definitely give it more reading if this is the first time you're being introduced to it. Okay, let's continue and let's discuss about the general nonlinear function, and we shall discuss about how to solve it, how to solve the least squares solution of that nonlinear function. So before we move forward, let us define what we actually want to solve. So we'll have a state x. We call it a state or an input. So x will be a vector of m variables, you could say. So x will be a vector of m variables. Just like we had in the system of linear equations thing. Similarly, we'll have x be a vector of m variables. Then we'll have a function. The function will be a vector of, so it will be a set of n. We say n, like let's suppose n functions, and each of these functions is like, it outputs k values for x. So it outputs a k vector, um, and k can be different for every function, right? So yeah, is there any confusion about the functions? It could be a little confusing, so I'll just explain again. So we have the main function which has n functions inside it. It's a set of n functions, f1, f2, fn, and each function f1, f2, fn outputs a vector instead of just one quantity, right? So now we have the observations. What are the observations? These are this is a vector of, it's a set of n observations. What basic observations basically are is that, so when we were solving the linear equations, the system of linear equations, we had ax equals to b, right? And if it was not so if b didn't lie in the column space of a, then there is no x for which you can multiply with a and get b, right? Is there any confusion here, or like are you following me till here? Okay, so there's no x which can be multiplied with a to get b vector, right? So in a sense, b vector are ground truth observations, right? And we want to find an x that when multiplied with a, or we want to find an x which when applied a function over yields us b. We want to find this x, but it might not be possible because yeah, it's perfect. It's perfectly fine to not be possible to find an x that when applied the function that we have been given over yields us b. It might not be possible to find an x like that. So we'll find the x that best, which gives us a b star which has the minimum distance from b. Excuse me. Right. So we'll find such an x that gives us b star that has a minimum distance from b. This is minimum. So yeah, instead of b, I'm using the z notation here because b will be used for something else later on in this section. So yeah, observations are z now. I hope it's clear till now. If it's not, you can ask. Otherwise, I'm moving forward. So yeah, you'll notice that we have n functions and we have n observations. And notice that each function is a vector. So each observation also will be a vector. First, and the length of that vector will be corresponding to the length of the vector of the function. Right? Okay. I'm assuming you understood everything up till now, so I'll move forward. If not, you can interrupt at any time. So yeah, so we need to understand what the problem here is basically. So if we have, so yeah, just like I explained in the previous slide, if we wanted to find the exact solution of fx equals to z1, f1x equals to z1, f12 equals to z2, if we wanted to find the exact solution of this equation, then it would be expressed something like this, right? Because we need to find an x which, when plugged into this function, yields exactly z1. But sometimes it might not be true. In fact, many a times it might not be true. And in that case, we use least squares approximation. So what happens in least squares approximation? We plug in the value of x in the function that we have been provided. We get a value of z star. We compare it with the observations that we have been provided, and we try to reduce this difference. So yeah, this vector modulus we try to minimize, if that makes sense, right? So yeah, let's start with the optimization problem then. So yeah, so the problem, we'll define the problem now. The problem is that we need to find an x. We need to find an x that minimizes z minus fx. So in the previous slide, if you look carefully, z1 star is equal to f1x, z2 star equals to f2x. So z star will be equal to fx, right? So we need to find an x that minimizes the modulus of z minus fx. Or we could also write it as we need to find an x that minimizes z1 minus f1 modulus squared plus z2 minus f2 modulus squared up till zn minus fn modulus squared, right? So we need to find the x that minimizes this function. This whole thing and this are equivalent. This is the same thing written over for clarity. So let's look at some more definitions now. We'll define the error d1, di, which is a function of x, to be zi minus fi x. So just a warning, heavy, so buckle up for that. But yeah, the error of, so we'll define the error di to be zi minus fi, where I varies from 1 to n. We'll define the squared error ei of x equals to the modulus of di squared, right? It makes sense, right? The squared error should be the modulus of di squared. Why I'm saying modulus of di squared is because this is not a scalar quantity, this is a vector quantity. So you really need to take the modulus of it before you're squaring it. And when another way to represent this is di transpose into di. You can multiply and check any vector with its transpose, and you'll get the modulus of that vector squared, modulus of the vector squared. So yeah, that's how we find the squared error. Define the square error. We then define the global error function to be the sum of all the squared errors. So for I from 1 to n, take every observation you have, subtract it, subtract the initial. So you have to take an initial guess. I forgot to mention that you have to take an initial guess like you did in the previous example of Newton-Raphson method. You have to take an initial guess, and that is what is written over here. This x is an initial guess. So yeah, right. So what we do to find the global error function f of x is that we take an initial guess, we subtract it, we plug it into the function, whatever we get, the output z star or fx, we subtract it from the observations, we find the squared error by taking the transpose and multiplying with the with itself. We find basically the squared error, and we sum all the squared errors together. So yeah, so this becomes the global error function is basically the sum of squared errors. If anyone has lost me, couldn't follow, I wasn't very clear at some point, you can ask. Right. So yeah, so the global error function is basically this. What I've written over here and what is written over here are exactly the same things. Even from the previous slide, what I wrote over here, this is the global error function. So basically what I want to say is find x that minimizes the global error function. Find x that minimizes fx is what I want to say. Right. How do we go about solving this? So we take an initial guess like we did in the Newton-Raphson method. Take note here that we are approximating the error as a linear function and not the global error function as a linear function. Why we are doing that, we'll get in that a little bit later. So yeah, we'll approximate the error di as a linear function. Using di, using the linear function approximation of di, we will construct fx again using the linear approximation, and will minimize that fx. Once we find the minimum of fx, we hope that, like, once we find the minimum of the fx of the approximated fx, we hope that this minimum is closer to the actual minimum of fx. And if so, yeah, if it is not, we keep reiterating using this new solution as the initial guess. We keep iterating until we find a good enough solution. Right? It's a fairly similar approach with a little bit of difference in these 2 points, but yeah, it's a fairly it's a fairly similar approach to the Newton-Raphson method. Right. So let's talk about linearizing. So when we said, so taking an initial guess is easy. We take any random, either random or a guess with some confidence. We'll look into that later maybe. So we'll start with approximating di as a linear function. So how to approximate the error as a linear function? So we take the initial guess. We want to find a delta x that we add to the initial guess, such that the error function, such that if we later find the minimum of fx. But yeah, so how do we approximate this as a linear function? We take di of x plus delta x. It approximately equals to di of x plus the Jacobian. Is the Jacobian. Could you just wait a second? Sorry about that. So yeah, we approximate the error function as the di of x plus the Jacobian of x into delta x. What is the Jacobian? It's basically, you could call it a derivative in terms of matrices. So when you take the first derivative so when you differentiate in matrices form, you get the Jacobian. You could think about it like that if you're not familiar with the concept of Jacobian. I'll link reading resources about Jacobian after the reading group, but it's not very important to understand Jacobian right now. You just need to know that it represents the first derivative in like matrix format. I also explain what the Jacobian looks like right down here. And from now on, we'll be referring to dix as just di, because it's now associated with the initial guess, and for a single iteration, initial guess won't be changing, right? So we'll just call it di. It will make things a little bit easier on the I. Also, we'll call it jix to be ji, and everything else similarly I'll abbreviate. Okay, so let's look at what the Jacobian looks like right now. So this is a Jacobian of the ith function. Uh, so you could say that it's the Jacobian of fi. It's the Jacobian of fi.
So if you don't know about Jacobian, I'll try to link you some reading resources. Yeah, you can read more about it. But just to get an idea of what a Jacobian is, you can think of it that it contains the information of the derivative of a function. So any kind of function, not necessarily, it doesn't have to be necessarily a 1D function. So if it were a 1D function, the derivative would just have one element. It wouldn't be a matrix like this, right? But since we have a function that outputs a vector, and also the input to that function is a vector, that is why we have the Jacobian outputting a matrix. So the number of columns in the matrix will be will correspond to the number of inputs that we have to the function, and like the number of elements in the input vector that we have to the function, and the number of rows of a Jacobian corresponds to the number of elements in the output vector of the function. So yeah, so you can see that the Jacobian has the information of the derivative of each element of the output vector with respect to each element of the input vector, right? So if we have a function which just takes one input and gives one output, then the Jacobian of that function will just be the derivative, like the first derivative of the function, like we all know. If we have a function that takes an input vector and spits out a single value, then the Jacobian of that function will be its gradient. But if we have a function that takes an input vector and also gives out an output vector, then the Jacobian of that function will be a matrix like the one shown here.
Okay, so that is what the Jacobian is, and so all you need to remember right now, if you're not very familiar with Jacobian, is that this is the Taylor expansion of the error function. Okay. So let's so now that we have approximated the error function, we can move on to approximating the squared error, right? So we have ei of x plus delta x. If we remember from the previous slides, ei was di transpose into di. So that's what I have written here. And if you simplify that using the approximations of the previous slide, you get this form, and excuse me. And when you take the transpose inside the brackets and you multiply them together, you get this. So what really happened here was that you just took the transpose inside the brackets and you just multiplied them both. So you got d1 di transpose di plus di transpose ji delta x plus delta x transpose ji transpose di plus delta x transpose ji transpose ji delta x, right? Okay, this might look a very long equation, but you can factor it a little bit by observing that this and this are essentially the same thing. Can anyone say why they are the same thing? Anyone? Any guesses? Can you notice any relationship between these two matrices?
They are transposes of each
Transposes
other.
of each other.
Right, they are transpose of each other. But you'll also notice that EI is a scalar quantity, right? So this is a scalar quantity, and this is also a scalar quantity, and they are transpose of each other. So you can basically say that these two are same. So you could just write it as twice of one of the quantities. Does that make sense? Is anyone there? Do I need to explain this?
I didn't get that.
Okay. So this EI is a it's the squared error, right?
Yeah.
So it's basically the modulus of the DI vector squared, right? So the modulus of a vector squared is a scalar, right? It's not a vector or a matrix. It's a scalar quantity.
Yeah.
So every one of these terms will be a scalar quantity because these are equal to the square error, right? And because these two are scalar quantities and transpose of each other, you can basically say that these two are equal, and you can write them as twice of one of the quantities. Okay. So I think that should clear things up. And now we look at this is a constant with respect to delta x, so we just write it as Ci, and this is also a constant with respect to delta x. We write it as Bi transpose. We just substitute it to be Bi transpose, and we also see that this matrix is also a constant with respect to delta x, and we write it as Hi. I think there shouldn't be any problem here, right? This is simple substitution, right? So now I'm moving forward. So yeah, all of that was the approximation of the squared error. Now we'll just sum over all of the squared errors, and the sum over all of the squared errors, and find the global error. So yeah, we'll sum over all the squared errors, and we can basically send the summation. We can break it up into summation of Ci, 2 into summation of Bi, right? We can take 2 and delta x common. We can take delta x transpose, delta x common, and we can say summation of Hi, right? And after we do that, we say that summation of Ci, we'll call it as C. Summation of Bi transpose, we'll call it as B transpose. Summation of Hi transpose, summation of Hi, we call it as H. So now this equation that you see right here, this expression is the approximated form of the global error function. Now, how do we find? So yeah, what you'll notice is that it's something like ax square plus bx plus c, right? Something of that form. This is what it's called quadratic form, if I am correct. It's called a quadratic form, and the solution of a quadratic form it's pretty similar to how you solve so to minimize a quadratic form, it's very similar to how you minimize a quadratic polynomial. You differentiate it once, you find the first derivative, and you set the first derivative equals to 0. So in this case, it will be 2ax plus b equals to 0. You find x equals to minus b upon 2a, right? So we'll do something very similar with this quadratic form in the matrix format. It will be a little bit fishy, but you'll see it will work out in the end, right? Oh, okay. I think I need to erase a lot of these. 1 second. Okay. So yeah, we express the global error as this expression over here, and just to remind ourselves what V transpose stands for, we'll just expand it over here, and we'll also expand H over here. You'll see why I'm expanding these over here, because these will be key later on, the key terms later on. Okay. So now that we have approximated the global error, so first of all we approximated the error function, then we use that approximation to approximate the squared error, and use that approximation to approximate the global error. Now that we have the approximate global error function, we will now begin to minimize it. How would we minimize it? We have found the global error function in a quadratic form. We have already done that. Now we'll find the first derivative of the global error function with respect to delta x, because delta x is the variable that we are considering right now for the approximation. And we'll set the first derivative to 0, and we'll solve for delta x. Does that make sense?
Yep.
Okay. So to minimize the global error, let's start with differentiating the global error function with respect to delta x, and we'll set that to 0. So yeah, I just replaced the global error function with the approximated form, and I broke up it into 3 derivatives. So this is the first term, the second term, and the third term. You'll see I just replaced the terms. I didn't do very much in this step. Now pay attention, as the next step might be a little you might not have seen it before. If you haven't read about how to differentiate matrices, how to find the first derivative in matrices, just assume that whatever it is written here is true. Yeah, so derivative of delta x transpose h delta x upon partial of delta x, that just turns out to be h plus h transpose delta x. That's just how it is. And the derivative of b transpose delta x, it turns out to be b, and we have the 2 in the outside the derivative. And the derivative of a constant term turns out to be 0, like it always does. Right. Now, can you say how this happened? Can anyone guess how that happened? Or can anyone say how that happened?
Is it a scalar again?
No, it's not a scalar. So what basically happened here was that I took
H is J. H is J plus J transpose, right? Or am I wrong?
H is J. Okay. H is J transpose into J.
Okay.
So what basically happened here was that I took H plus H transpose and I wrote it as 2H. So if we cancel out H both sides, we get H transpose equals to H. So what is this kind of matrix known as? Symmetric, right? And we can see that from this equation over here, because we can see that from the equation over here, because so yeah, it's the sum of over all Ji transpose Ji. So each of these Ji transpose Ji will be a symmetric matrix, right? Because if we take a transpose, I think it will be symmetric, right? Yeah. I think yeah, it will be symmetric. Correct me if I'm wrong, but yeah, I think it will be symmetric. Yeah. So because H equals to the sum of Ji transpose Ji, the sum of H with its transpose comes out to be 2H. And now we have simplified this equation quite a bit. Now all we are left with is 2b plus 2h delta x equals to 0. All we need to do is now find delta x. So we find delta x by simply cancelling out 2's both sides, and add negative b to both sides of the equation, and we get s delta x equals to negative b. And now we can easily solve for delta x by inverting h and multiplying on both sides on the left side of the equation, like on the left side of the variables, and we find delta x equals to minus h inverse b. Again, in practice, we don't really take an inverse. We use other forms of matrix solving methods, like I think some of them are called, if I remember correctly, sparse normal Cholesky form and dense Schur form. I'll add some links if you want to explore them in more depth. But yeah, so right. So now that we have found our delta x, all we need to do is now update the value of the value of the initial guess and check whether the value of the function at the updated value is is it the solution yet, or there needs to be done, like more iterations needs to be done, just like we did in Newton-Raphson. We just updated the value of x and we kept iterating until the global error converges. I think it's clear till now, right? Is there anyone who has any doubt till now? Okay, so I'll proceed. Yeah, so that was about least squares. So before I proceed, I'll just point it out over here that the iterative form of this equation will be xn plus 1 equals to xn plus a delta function of xn, right? Because delta x was found to be h inverse of b. Both of these values depend on x. This is it has some of Jacobians with respect to x, and this has also some of Jacobians with respect to x multiplied with the d transpose or something. So yeah, both of these quantities depend on x. This whole thing depends on x. So yeah, the delta function is a function of xn. So yeah, we basically see that form again that I was talking about a few slides earlier. And yeah, it's a pretty common, I'd say it's a pretty common form of finding, iterating to find the solution. You see this kind of form very often, like these kind of problems. So let's discuss about weighted least squares. It's like very simple to do weighted least squares minimization. All you need to do is, for every observation that you have, just define a covariance matrix. So for every observation, just define a covariance. I believe this is the sign for covariance matrix. For every observation, just define a covariance matrix and invert that, and you get this matrix, omega matrix. And just sandwich it between the error transpose and Jacobian while calculating B transpose, and sandwich it between the Jacobian transpose and Jacobian while calculating the H matrix. Now, why this is true, you can look at the derivations of this form of weighted least squares. over at, like, I think all of you should know at this point about this guy. Pardon me if I spell him wrong. Cyril Stackness. Cyril Stackness does he's a professor, and like, he does, so he has he's been working in photogrammetry and geometric computer vision, and he uploads lectures sometimes. He uploads lectures very often, and one of those lectures are an informal introduction to least square minimization or least square solution. So I'll link that video later on. But yeah, most of my content I borrowed it from him. I borrowed it from his slides. But yeah, I didn't want to include the omega while talking about the least square minimization, because I felt that was too confusing when I was going through it first time. But I think now that once you have an understanding of a little bit understanding of least square solution for non-linear functions, I think yeah, you can have a look at the weighted least squares derivation that Cyril Stackness did on his informal introduction to least squares minimization. And yeah, omega is the inverse of the covariance matrix corresponding to the observation Zi. Okay, so yeah, that's how you add weights to least square minimization. Why you need weighted least squares minimization is, like, for example, if you have if you trust some of your observations more than some of the other ones. So if the car was moving at so if you have a camera mounted on a car, and the car was moving at a speed of 10 meter per second, when you captured 5 pics, and then you captured 3 pics, and the car was moving with a speed of 20 kilometers per hour. It was moving with a speed of 100 kilometers per hour. And I think because of rolling shutter and errors like that, you would want to keep pictures in which the car was moving slow if you are doing some kind of 3D reconstruction or something. Because those have lower error. You have better confidence in those images to be accurate. So if you trust some of the images, some of the observations more than the others, then in that cases you need weighted least squares. And yeah, in weighted least squares, we assume it to be a Gaussian distribution for all the observations. Okay. So yeah, we are coming towards the end of the reading book. We'll just look at one example and then we'll finish off. I wanted to touch upon bundle adjustment today, but unfortunately I couldn't get time to prepare the slides or the content. So I think we'll finish off after this Python example. So consider the problem where we have 2 dimensions in the state in the state variable. We have the functions f1 equals to x1 square x2 and f2 equals to x1 x2. So we have f1 equals to x1 square x2 and f2 equals to x1 x2, right? So in this case, I just took f1 to be a single dimensional vector instead of multidimensional, because that makes life a lot easier, and also lets me do some kind of a visualization that you guys will see later. So yeah, we have f1 equals to x1 squared x2 and f2 equals to x1 x2, and fx equals to it's a set of the 2 functions, and the observations that the observation that corresponds to the first function is 12. So we need to find such an x that when plugged into f1 yields an output 12. And we need to find such an x that when plugged into f2 yields an output 6. We can very easily see that the solution should be x1 equals to 2. So like you could divide f1 by f2 and you get x1 equals to 2 and x2 equals to 3. It's very easy to solve it analytically, but we're trying to solve it. So now that we know the solution, we know where the convergence has to occur. I think it will be a little bit more exciting to see the Python program converge to that value. So yeah, I'll just write it over here. X1 equals 2 and x2 equals to 3. Is we know that this is the solution, but we still want to find it using non-linear least square approximation. So yeah, so we have to find the value of x that minimizes z minus fx. Okay, so what is the solution? It's basically I just go through each step with all the values plugged in. So the Jacobian of first function will be like differentiate with respect to x1, you get 2x1, x2, differentiate with respect to x2, you get x1 square. Similarly, Jacobian of second function will be x2, x1. The error function will be 12 minus x1 square x2 and 6 minus x1 x2, right? So yeah, now we have to approximate the error function, but yeah, so I'll skip over all these steps that we did in the derivation, and I'll straight up jump to this guy, B transpose, because all we need to find a solution are B transpose and H, right? So I'll straight up come to that. I'll straight up find B transpose equals to D1. So the formula was summation of DI transpose JI, right? So this is what I've written. And you plug in the numbers and you find B transpose to be the transpose of this matrix. You find B to be this matrix. You find, so now we want to find H1. We want to find H. That was summation of JI transpose JI. So that's what is written here. And you plug in the numbers, you find H equals to this expression over here. Right. So now that we have, so now we found B transpose and H. And we can, like we found B and H, and we can easily find minus H inverse of B. So delta X will be minus H inverse B. But let's look at the code for this. I think that will be right. So here I have the code for that problem. Here I have f1 equals to this. So f1 equals to x1 square into x2, and f2 equals to x1 into x2. I also defined the Jacobians to be what I calculated in the slides. And I also defined the error functions. So this E1 should actually be D1. That was my bad. I should have kept consistent variable names. Let's just change that real quick. E1. Change E2 to E2. Yep. So I think that should not break anything. Right. So I also defined the error functions to be like the observation minus f1x, observation minus f2x. Okay, no problem. Okay, so now we have. So I define the number of iterations. So okay. So is my screen like readable at this size, or should I zoom in a little bit?
It is readable. Yeah.
Okay. Okay. So now we have. So I defined the iterations to be 3000, but it will converge much before reaching 3000, and I have kept a condition for that. I take the initialization to be I take a really bad initialization just to show you guys how the gradient descent actually works. So it's a kind of gradient descent only, right? Because yeah. So I have taken a really bad guess just to show you how the gradient descent works. And yeah, I have defined the observations to be 12,6 like we had in the problem. R is just the size of the image. You can ignore all of the code from here to here. This is just the code for visualization. Also ignore this code, which is also for visualization, and this code is also for visualization. What you want to look at is this part. So I just found the H matrix over here by using NumPy with the Jacobians, and I also found so yeah, this over here, this NP transpose till here, this is the B matrix and divided by H, right? So because divided by H here works because in this case, in this particular case, H was a scalar quantity, but it need not be a scalar quantity if your functions have vector outputs. So in this case, H was scalar quantity, so I just divided by it. It won't let me do a matrix inversion operation on that, so yeah, I just divided by it. And I incremented the initial value with the delta x that we found from that, and I printed along with the number of iterations that have occurred so far. And so if any iteration, the global error function becomes less than 0.0001, I'm just breaking out of the loop and calling it I'm saying that it's done. It's a good enough solution if the global error reduces below 0.001. That's my convergence criterion, you could say. Yeah, so that was the code. It's a fairly simple code. It's just I think 1, 2, 3, 4, 5, 6 lines over here, and 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Yeah, so it's under 20 lines, and yeah, I'll just show you how this runs. Oh yeah, so I forgot to explain. What we'll visualize here is an image, and on that image will be, so there'll be two axes, x1 axis and x2 axis, and the colors that we see in the image correspond to the global error that we get if we plug the values of x1 and x2 at that coordinate into the global error function. Does that make sense? So this is the image that I was talking about. So this axis is so x1 is 2, right? Right. So this axis is x1 and this axis is x2 downward. And this image corresponds to the global error function at each coordinate. So for example, at this coordinate, if I take the value of x1 and x2 and plug it inside the global error function, what I will get is the what I will get. I'll convert it to an RGB color image and show it to you in this plot, right? Can someone tell me where, by just looking at this image, can someone tell me where the minimum of this function is?
That black part.
Inside what color?
Inside the green one.
Right. So this part you're talking about, right? So if you look really closely, this point is the point of convergence. This point is the minimum point of of this global error function, right? So if I run the iterations, you'll see the iterations down here. I'll just zoom in a bit. So yeah, if I run run the iterations, the iterations will start at some point, and then they will rapidly fall towards, fall along their gradient, and yeah, they'll be basically, it's basically a gradient descent towards the minimum of this function. So I'll run the iterations now and look closely at the white line that is being drawn. It's not being drawn yet. I'll start the iterations now. So yeah, at 1100 iterations, it has reached a solution of 2.003 65854 and 2.98971681, which is I think a pretty good solution for like we know that the correct solution was 2,3, right? So it is pretty close, And if I add more iterations and add more accuracy to my conversion criterion, it will even be more accurate to converge. So I'll just run it again just to show you. This was 1100 iterations, right? Right. So now this should be more accurate, and it should take more iterations to converge because I increased the conversion criterion accuracy. Already crossed 1100. Yeah, it converged at 1300, and it's now 2.001 and 2.996. So you can see that it is more accurate. Also, I'll show you with a better initial guess. I say. Yeah, this is a better initial guess. It's so you'll see that the white. So yeah, this took 1300 iterations to converge, but this should not take 1300 iterations. It should converge in much less iterations, and yeah, it should converge in much less iterations. Right. So it converged in 1,000 iterations. So yeah, so you can see that it really started out not being on this blue region. You can see there's a dot over here. If you look very closely over there, I think, can you see that dot? Is it visible in your screen?
I don't think so.
Okay, I'll just take a screenshot real quick.
Where?
Yeah, one second. So this is the dot I was talking about.
Okay.
Yeah. So it starts out not being at the blue line, but it converges to the blue line so rapidly that you can't even see the trail. Right? It's so far apart. So that's what is kind of an advantage in using this method, is that if you have if the gradient is absolutely telling you to go in a certain direction, it will take the number of steps are, so it's a good way of doing a gradient descent. It's a good way of choosing step size rather than just choosing step size. So imagine if you took constant step sizes doing this gradient descent, where would that lead you? You wouldn't even have been. So if you started out here, you wouldn't even have reached over here in the amount of iterations that it converged. So it's a pretty good way of calculating step sizes. Yeah. So just for letting you know what a good solution is, I'll do this again with 4, 4 as the initial guess. Now, what do you think will happen if I use 4, 4? Will it be a worse initial guess or will it be a better initial guess?
Should be worse because it's further, right?
So let's run the simulation and let's run the iteration and let's see what happens. So you said it would be worse, but it's actually much better.
Maybe the slope is greater there.
Right. So if you initialize at 4, 4, it directly falls inside. So if you imagine a ball rolling, the ball directly rolls to the minimum of that pit. While if you initialize it at 2.5, 2.5, the ball initially rolls to the side and then slowly rolls towards the center. If that makes sense. Does that make sense?
Yeah, got it.
Right. So yeah, if you can't really say based on like Euclidean distance between the initial point and the expected output as to whether it is a good initial guess or bad. But yeah, obviously if you choose an initial guess like 1000 or 1000, it will be, I think it will be worse. But yeah. So yeah, this is all I wanted to convey in this reading group. And yeah, if you have any questions, you can ask now, or if you come up with questions later, you can ask them. You can ask them on Discord or Messenger. Do you have any questions right now? Is there any part of the reading group that you did not understand?
I'm still not sure about that part because the part where you said that squared error is equal to absolute error only, like we'll get the same result. But I remember reading that they are different, aren't they? For example, if you have one outlier, then you get like different. Then the squared error gives very different results than the absolute error. Because then the outlier.
What do you mean by absolute error?
I mean, if we minimize mod of di and di square, like
right,
sigma mod of di or sigma di square,
right,
they'll give us.
Oh, right. Okay, yeah. So I made. So yeah, that's my bad. Where did I? What side was that? I think it was this side.
Yeah, no, it like it wasn't in a slide. You wrote it with a pen, so yeah.
Okay, yeah. So I think I should be. I should have mentioned it somewhere, right? Yeah, I mentioned it over here. I remember now. So yeah, this is my bad. There should be a square over here. Should be a square. That's my bad. Thanks for pointing that out. Also, that will be a square in a later slide in
Yeah. Okay.
bundle adjustment, not bundle adjustment. Let me just fix the slides now.
Yeah, I got it.
Yeah. So, any other questions apart? Like this was a good point. But yeah, any questions apart from that? Anyone? Okay, I think if there are no questions, then I think yeah, we should conclude the reading of